Next speaker, we have Joshua Rule presenting Learning as Programming, Modeling Efficient Search and Human Concept Learning.
Bear with me for a second here. All right. Hi. Thanks for being here. I'm going to talk today about a project I've been working on with Steve Pianadosi and Josh Tenenbaum. And what we've done is we've tried to develop a model that explains human behavior during learning better than some recent alternatives. And the big idea is that we can represent a concept not only in terms of its content, but also in terms of the inferences or the pattern of reasoning that we use to produce that content. And by searching over both kinds of representations, we can learn faster. So let's start by looking at two lists of numbers. So what rule could transform the list on the left to the list on the right? If you think you know what it is, just raise your hand. I'm not going to call on anybody. I just want to see how kind of it percolates through the room. Okay. Now, what if I swap the right-hand side to this one? Go ahead and raise your hand again. Okay. This one? Okay. A couple more here. All right, it takes a little bit longer. And how about this one? You're like, okay, just give me some more examples. So these are examples of list functions, just functions over lists of natural numbers. And I'm happy to say more later, but the thing to hit on right now is they have this long history in AI, but they're not super common in psychology, even though they combine many of the best traits of classic concept learning tasks from psychology. So let's imagine we want to model what's going on while you're learning one of these things. So one natural approach would be to consider neural networks. You know, they produce great performance on all sorts of different tasks like game playing and structure prediction, but they typically struggle to learn from limited training data, like you did that with one example, to compose well or to generalize easily to new tasks. So, you know, they're often at human level, but rarely human-like. Another approach we might consider are language of thought models. So these represent concepts as expressions in something like a mental programming language. And they explain how we acquire things like motor programs or how we solve visual puzzles like Vanguard problems. And they do tend to acquire human-like solutions from just a few examples, but they are also really difficult to scale to human-level performance on kind of complex tasks. So sadly, neither approach here is both reliably human-level and human-like. And that kind of tension receives a lot of attention in neural networks, but we're going to look instead at improving these language of thought models. And the primary reason that they perform poorly is search. So if you're trying to pick one program out of the space of all possible programs, that's really hard when your space grows exponentially in the complexity of the language of thought you're trying to model. So existing search techniques just can't keep up with the combinatorial explosion. And our general approach to improving search was to look at the behavior of human programmers, reasoning that if learning is something like programming, then the way that people navigate program space might tell us something about how they navigate concept space. And we wrote a paper for TICS about this called The Child is Hacker, where hacker is just shorthand for human computer programmer. And this led us to three kind of core insights. So the first is that programmers have cataloged hundreds of useful search techniques that are custom tailored to do things like extract or transform loops into recursion or extract repeated structure into a function. And unlike many existing language of thought models that apply a single general purpose technique at scale, programmers seem to rely on special purpose techniques that are deployed at just the right time. And the second insight is that while code is one way to represent a program, you can also represent it as a composition of the search steps that you use to produce that program. So that seems to be how many programmers think about their work. It's not so much about the individual symbols that they're typing, it's about the search steps that they are going to apply, big kind of chunks of behavior over time. And the third thing is that when you have techniques for identifying latent structure, like these, then you want to start with as much latent structure as possible. So unlike a lot of existing models that start by just taking the first derivation from the grammar or a random sample, those things aren't going to contain a lot of structure about your problem. You want to start with something like the data, which has all the latent structure that you have. So we implement these ideas in a model called HL, which stands for hacker-like. And it extends a user-provided language of thought with additional operators called metaprimitives. So you give me your domain primitives, the things that you care about, and then HL is going to glom on some additional search operators. And these metaprimitives are basically rules for transforming programs. And so that means that HL can combine program structure, domain structure, and search structure into one kind of expression. And so it's much more flexible than previous approaches. And to see how this works, assume that HL has data like these for a function that simply appends and prepends a few elements to its input. Now, rather than discover a program by enumerating or randomly sampling, which are kind of the standard approaches, HL is going to incrementally build a metaprogram, which is a combination of domain primitives and metaprimitives. And one of our key metaprimitives is this one that I've highlighted, memorize all, which memorizes the observed data. So it takes the data that you know about and it imports it directly into the program. So you have access to that structure and future metaprimitives can operate on it. And whenever we execute a metaprogram, we get a program, which is what I'm showing in the purple box. And then we can evaluate that thing against the data. So we're going to build metaprograms, run them to get programs, and then we'll evaluate those. And HL can continue this process, just extending and revising its metaprogram until it finds a simple and general solution. And that's the gist. We're going to take a domain-specific language, and then we're going to extend it with domain general search techniques. And we use MCMC over trees to do the actual search over metaprograms, if you know what that is. But if not, it's a pretty common technique in this sort of model. And so we're improving search not by changing the search algorithm, but by embedding search operators into our representation language. Okay, so to evaluate HL, we built a game where participants would learn list functions by repeatedly seeing inputs and being asked to guess the outputs and then get feedback. And we organized that game into rounds of 11 questions each. We had 10 rounds, one for a different function in each round, and collected data from about 400 people on Mechanical Turk. And using this setup, we tested 100 different list functions, and we designed them to vary widely in terms of their algorithmic content and kind of how difficult we expected them to be to learn. Here are 6, along with the mean accuracy across all trials for people. And here's how people do on all 100 functions. So what you're seeing here is the empirical distribution over accuracy on the y-axis, and then functions across the x-axis there. And mean accuracy is reported in red, and these 6 functions are marked in blue. And the main thing to see here is just that there's a lot of variance. So some are really very easy, some are quite difficult, but there's a nice spread in between. Okay, so we compared HL to 4 alternative models in trying to explain that human data. The first model exhaustively enumerates every program in the language. And this approach actually does a pretty good job of predicting learning for things like Boolean functions, which is why we include it here. The second is a form of stochastic search that samples programs from a posterior. And the specific model is Fleet, which is a high performance implementation of MCMC. The third is a form of proof-guided search. So you represent the problem as a logical theory with some variables that you need to instantiate in order to solve the problem. And we specifically use Metagol, which is a first-order logic system. And the final model is called RobustFill. So it trains a deep network on millions of programs and input-output pairs to produce a distribution over programs conditioned on data. And it sometimes outperforms these other symbolic models, which is why we've got it here. Okay. Here's our first result. So humans are in black and models are in color. And each point represents the number of functions acquired by the median learner by a given trial. And acquire means they've made their last mistake. So you're going to have perfect performance from now on for a given number of functions here. And people are very good at this task. They acquire about 50% of our functions within 7 trials. HL and Fleet, which is a stochastic search algorithm, also have slightly better than median human performance here. But the other 3 models are much worse. They only ever acquire about 20% of the functions. And we can also ask, so, okay, how well are these models doing at predicting mean accuracy for each function? And that's what you see here. So the y-axis is tracking the ratio of model to human performance, and each point is an individual function. And the crossbar there is the median. And these results tell a similar story, which is nice to see. Now, we computed these results by letting HL and Fleet each generate about 500,000 hypotheses per trial. And the other 3 algorithms, we actually gave them a lot more leeway. Some of them were generating like tens of millions. And those numbers seem implausibly large. So this may not actually be the right comparison to make. So what if we drop the number of samples collected by a couple orders of magnitude? And here are those same plots for HL and Fleet, but with 100 times less search. And you can see that HL still looks similar to people, but Fleet's performance drops significantly. And we can actually push HL even further. So these subplots are labeled by the number of steps per trial. And you can see that even down to just 50 steps per trial, HL's performance is remarkably robust. And now we've got something which is like plausibly human scale in terms of the amount of search that it's doing. And the question is, okay, so why does HL work so well when it has so few resources? And we think it's because these meta primitives reparameterize the space of hypotheses to make it easier to say useful things by leveraging the information that you already have in the data. And this plot confirms that idea. So we're comparing the complexity of a metaprogram on the x-axis with the complexity of the program that gets produced by that metaprogram on the y. And the dashed line shows where they're equal. And then the individual points are like the best programs that HL is able to find during search. And what we see is that over 80% of those points are above the line. So they're easier to describe as metaprograms than they would be to describe directly as programs. And so you might think, okay, so if these metaprograms are so effective, we don't really need to track program complexity at all. We should just pay attention to these metaprograms. But it turns out that both are necessary. So this plot shows how performance changes over time when HL ignores either form of complexity. So it's actually tracking both program complexity and metaprogram complexity in its prior. And when we drop either one of those things, performance also drops. So they capture slightly different ideas about simplicity that are both useful for guiding search. Okay, last result here. So we also tested 2 recent large language models, GPT-3 and Codex, where Codex is a version of GPT-3 that's been trained on billions of lines of code from GitHub. We don't include them in the kind of the core model comparison just because they're not plausible models of human learning, like that they have vastly more training experience than any human would. But we asked both of them to directly predict outputs given inputs. And we also, because Codex has kind of programming training, asked it to write Python programs that would predict outputs given inputs. And here are those results with HL below. And given the amount of training experience, we'd expect these models to perform way better than the median human. Hopefully for some of these code production tasks, we would see Codex kind of as good as our best humans, but that's not the case here. They generally underperform the median, and even kind of the best model, the best performance here is less accurate than HL and less accurate than the median human on most trials. Okay, so just to summarize, we've introduced this theory, a formal theory of learning that's based on explicitly representing search techniques as metaprimitives in your language of thought. So we're essentially extending the idea of learning as programming to learning as metaprogramming. And we found that this approach predicts human learning better than several recent alternatives. And given all that, it seems plausible that humans might be using a variety of search techniques like this in their own learning. And if that's so, then the complexity of inference, or like the complexity of the pattern of reasoning that people are going through, helps to explain learning difficulty independently of the complexity of the thing that's being learned. And so the metaprimitives are just really dramatically reshaping a learner's inductive bias. Now, HL is, I think, a first step toward even more realistic models. And I think that we can increase the number and the sophistication of the metaprimitives that we have implemented, and that would allow us to track increasingly complex patterns of inference. One of the things I'd really like to do is focus on metaprimitives that might help explain conceptual change. So if we start with some system, how do we introduce totally new symbols into that system? And I'd also like to develop a search algorithm that's less stochastic, that's not fundamentally MCMC at bottom, but something more human-like, where it's capable of telling you which small number of metaprimitives it thinks it should try next and give you reasons as to why those might be the most useful. And I think that doing those kinds of things could pave the way toward making this idea of learning as programming a much more comprehensive theory of learning. And I think we have time for just a couple of questions. So thanks for listening.
It looks like we have a virtual question. It says, great talk. When it comes to brain real, one possible problem about search-based framework is that human memory limitation doesn't allow for holding a vast amount of search results in the head. What are your reactions to this?
I think that's right. So previous versions of this algorithm had used, or of this model had used an algorithm called Monte Carlo tree search, which does require you to maintain a huge number of previously visited hypotheses. And that was a significant limitation. I had to run that model on machines with huge amounts of memory because otherwise things would just crash. One of the nice things about MCMC is you're really only tracking a very small number of hypotheses. So really one per chain. So if you're running a single chain, you only have to track the current hypothesis. And then maybe the next proposal that you're going to consider. And that's much more manageable to think that somebody has something in mind and they're going to consider, well, what might I go to next? That's a lot less to keep track of.
Hi, thanks for your talk. So I have a question about like the human-like learning part. So here you've showed like the human-like performance. And I was wondering like if you also sort of did some other analysis of like what kinds of meta programs were favored, or like what kinds of programs that were generated, and whether like you could measure or like analyze the similarity to like what sorts of like strategies that people were using, if that makes sense.
Yeah, so I don't know that we have the granularity in our human data to really answer that question well. There's one thing that I'm interested in doing, which would be running this experiment with an eye tracker so that we can see what aspects of the inputs and outputs people are looking at. Because I know that in my own experience, when I'm doing these things, I notice things like, oh, the input and the output are the same length, or the input and output elements are all the same, but they're in different orders. And that there are certain properties that I pay attention to that seem to give me a lot of signal. And I think if we could track those things in people, and then we could find a way to algorithmically take advantage of them, that would be a really interesting experiment to run.
Yeah, definitely. Thank you.
Yeah, sure.